Welcome to 12.1, which is Group 2 of the Alkaline Earth Metals. You need to look at your textbook, then it's pages 176 to 178. So our lesson objectives for today are to understand the trends in atomic radius, burst ionization energy and melting point of the elements magnesium and barium. Know the reactions of the elements magnesium and barium with water and recognize the trend. Know the relative solubilities of the hydroxide of the elements magnesium and barium, and know that magnesium hydroxide is sparingly soluble. Know the use of magnesium hydroxide in medicine and calcium hydroxide in agriculture. Know the relative solubilities of the sulfates of the elements magnesium and barium. Understand why acidified barium chloride solution is used as a reagent to test sulfate ions, and to know the use of barium sulfate in medicine. So first of all, we need to know where the group 2 metals are. On that periodic table it nicely shows it's the second, not the first column on the left, but the next one. So that's group 2, so you can see it's beryllium, magnesium, calcium, strontium, barium and radium. So we need to know the trends in physical properties of group 2 metals. So first of all, the atomic radii, which is hopefully an obvious one. The atomic radii increases as you go down the group, and the explanation for this is that each subsequent element has an extra shell of electrons. So because they've got an extra shell of electrons, the outer electron is then further away from the nucleus, which means the atomic radii is larger. The next trend you need to know about is melting point. The trend in melting point is that it decreases as you go down the group, and the explanation for this is that, as you know, the group 2s are metals, so they're giant metallic structure with delocalized electrons. And the high melting point of metals is down to the fact that you've got a very strong attraction between the positive nuclei and the delocalized electrons. So as you go down the group, the size of that cation increases. And what that means is that the attraction between the positive nuclei and the delocalized electrons decreases slightly, because the delocalized electrons are further away from that positive charge. So this means the strength of the metallic bond has decreased, which means that there's less energy needed to break the metallic bonds, so you have a slightly lower melting point. Now there is an anomaly in this trend in that magnesium doesn't fit the trend, and this is just down to the arrangement of the atoms being different, because that also affects the melting point. The next trend that we need to know about is ionization energies, and the trend in this is that it decreases as you go down the group. And the explanation for this is that each subsequent element has an extra shell of electrons, which means the atomic radii is larger, which means that the outer electron is further away from the nucleus. It also means that because you've got that extra shell of electrons, you've got more shielding. And both of these factors together outweigh the increasing nuclear charge, and therefore there's less energy needed to remove the outer electron. The ionization energy is less. Coming on the back of the ionization energy is the trend in chemical reactivity. Now the group 2 metals get more reactive as you go down the group, and the explanation for this is we just talked about the ionization energy. And group 2 metals, when they react, they're going to lose electrons. So when they react, they give up electrons to give positive ions. So when they do this, we've already said that the ionization energy decreases going down the group. So what this means is it takes less energy to create those positive ions. So because it takes less energy to create those positive ions, they're going to be more reactive. So therefore, the chemical reactivity increases as you go down the group. So as well as the physical properties, you need to know the chemical reactions of group 2 metals. So group 2 metals react with water, and these are redox reactions, because the metal goes from being an element with a 0 oxidation state to being a metal ion, so a cation is a +2 ion. So it means it has lost electrons, therefore it's been oxidized. Now, as we said, that these get more reactive down the group, so the reaction gets more vigorous. The general equation is that the metal reacts with the water to give metal hydroxide and hydrogen, which we can represent with this general equation where M is the metal. So that reacts with the water to give the metal hydroxide, and because it's in group 2, you need it's going to be OH2, there's 2 outside the bracket, remember, and you're also going to get the hydrogen gas with milk. The only other exception that you need to worry about is magnesium. So the magnesium reaction with water is very slow. It does happen, but it's very slow. With steam, however, we get instead of getting the metal hydroxide, we get magnesium oxide. We still get hydrogen, and that's represented by this equation here. So Mg plus 2H2O gives MgO plus H2. So you need to know about the hydroxides and the solubilities of them and the uses. So the hydroxides of group 2 metals are white solids, and they become more soluble as you go down the group. So as we start at magnesium hydroxide, that's almost insoluble. So when you have a magnesium hydroxide, we call it suspension. You can actually see it. And you may have come across this at home. It's used as a remedy for indigestion. So a suspension of magnesium hydroxide is called milk of magnesia. And it's called milk because it looks milky because you've got that suspension of the solid. So after magnesium, you've got calcium hydroxide, which is sparingly soluble. So it is soluble, but not very much. And we will have used, or you will have used, solutions of calcium hydroxide because a solution of calcium hydroxide is lime water. And of course, when you breathe through lime water, you bubble the carbon dioxide through it, you end up with the insoluble calcium carbonate forming, which gives you that cloudy white precipitate. Now, calcium hydroxide is also known as slaked lime, and we use slaked lime to treat acidic soils. So when farmers are growing crops, certain crops need certain pHs to grow properly, and calcium hydroxide or slaked lime is something we can use to get the pH right. So if the pH isn't very good, so if it's acidic and we need it not to be acidic, we can add slaked lime, and that will make it more neutral so that the plants can grow better. So then we've got strontium hydroxide, which is more soluble again, and barium hydroxide, which is soluble to give a strongly alkaline solution. So you also need to know about the sulfates, their solubility and uses, and the trend for this is the opposite to the hydroxides. They become less soluble as you go down the group, to the point that barium sulfate is virtually insoluble. And this is a good thing, because we use barium sulfate as a barium meal, which is where you want to take an X-ray. The person who's having the X-ray done ingests some barium meal, and the barium then absorbs the X-ray, so you can see the X-ray, you can see certain parts of it clearer. And the reason it's good that it's virtually insoluble is that barium sulfate is toxic, and if it was soluble, then it would cause you all sorts of problems. But because it's virtually insoluble, it doesn't get into your bloodstream in quite the same way, and therefore it doesn't cause you any major problems. The fact that barium sulfate is insoluble is also allows us to use this is a test for sulfate ions. So when you've got sulfate ions, you'll come across this test at GCSE. You acidify your solution with nitric or hydrochloric acid because that removes the carbonate ions, and then you add barium chloride. And if you've got barium there and you've got sulfate there, they will form a white precipitate of barium sulfate, and that tells you that you've got sulfate ions there. Now when you acidify with your acid, obviously you can't use sulfuric acid for that, otherwise you'll be providing sulfate ions and you're going to get the white precipitate regardless of whether you've got sulfate ions in the solution or not. So back to our lesson objectives. I've seen there's quite a lot of them, I'm not going to read them out again. But just have a read through them and just check that you understand them. And if you don't, as usual, go back and watch the video or use a textbook to help.